Welcome everybody to tonight's British Astronomical Association Muon meeting. Tonight, the 18th of May 2026. It's a pleasure to see you all, and thank you very much for joining us from so many different places in the world. That's wonderful. Tonight is going to be quite exciting because Dave Bracey is going to give us a more in-depth look at his cloud chamber. Last meeting he gave us a brief look, and certainly I'm very excited to see and find out more about that, which looked amazing last time. And if you have anything thereafter that you'd like to present individually, then in the same way that the Society of Amateur Radio Astronomers in their Drake's meeting and radio telescope observation parties go around everybody in the room and give everyone their own 5 minutes, I will do that for yourselves as well. So if you have anything to present, please feel free to do so at that time. There will also be an opportunity to ask questions of Dave once he's finished his chat. And Dave, you can have pretty much as long as you want, really, but 3/4 an hour to an hour is absolutely fine if you have anything as long as that. But it doesn't matter if it's shorter than that or longer. Okay, so I'll just pass the floor over to yourself. I'm going to start by muting everybody, so you probably will need to unmute yourself again, Dave. Just to say, tonight's meeting is on Microsoft Teams. Next time we'll be moving over to Zoom, so hopefully that will work. So I'm starting my muting now, Dave. Let's say you'll need to unmute yourself again.
Yeah, okay. Thanks, Andy. Hopefully everyone can hear me now. Yeah, so last time, as Andy mentioned, last time round, I gave a brief mention of a cloud chamber project I've been working on for a while now, with I suppose a particular reference to muons, which obviously is of interest to this group. So my plan for this presentation is to, first of all, I thought give a short talk about muons and what they are, a few essential features of them. I'm sure everyone in this group knows all this already, but thought it might be worth doing that for benefit of anyone that isn't, or people looking in, viewing the video later, just to give a little bit of background as to what it's all about. I suppose I should really qualify that by saying that I'm not a physicist, and I have no high-level physics qualifications. I'm a sort of R&D based mechanical, when I was working, I was an R&D based mechanical engineer. So as far as physics goes, yeah, I'm self-taught, just like I suppose many people here. So please bear that in mind for anything I say. And if you think I'm saying something that's not correct, then by all means, shout out and put me straight. No problem with that at all. Anyway, yeah, so I'm going to kick off by talking about essential features of muons. And then what I thought I'd do, I want to go into a little bit of history, actually, because muons, in the early days of atomic physics, and I think it really back in the sort of 1920s, 1930s, muons were actually an essential feature of the research at that time, as they were the principal source of high energy particles, which you need for doing research, as other sources which we now have didn't exist at that time. So muons were key. I'm going to talk a little bit about the sort of equipment that they were using back then, the 20s and 30s, and that's with reference to cloud chambers and the type of cloud chambers they were using, and the sort of things they were doing. So we'll talk about a little bit of that. I'll talk for a little bit about how those systems worked, why they worked, and why the particular sort of chambers they were using at that time were useful for muons, and other type of cloud chambers might be less so. And then I'm going to talk about my attempts really to. I'm not going to use the word replicate. That would be presumptuous, but let's say mimic the equipment that they were using. I tried to build something along the lines of what the guys were doing. I don't have anything like the ability on the brains or the technical backup that they had, but doing what I can do in the shed, see how far I can get with it, and I made a little bit of progress. So talk about that. And then so that's all sort of slideshow-ish, PowerPoint based. But what I want to do then is to sort of break away from that a little bit and to give you a live tour of my equipment. So go around it and show you the essential features. And after that, I'll try and fire it up and let you see it in operation, which might be of some interest. That's a little bit difficult for reasons we'll come on to later, but do the best we can. There'll be a little bit of expectation management on it, I think, probably the right words. But that aside, you never know, might go well. And to complement that, I've also got some video clips of some results that I've gained with the setup, so you can see, what I've got, what I've seen, and the sort of thing that goes on. So all right, okay. So all that aside, let's launch into it. So I'll share my screen now and do all that, and that one there, slideshow. Hopefully now should be seeing the slideshow. Is that what everyone's seeing? Oh, you're muted, aren't you?
No, yeah, yes, we are. Chasing Muon's David Bracey.
Thanks, Andy. Okay, all right, that's reassuring. Okay, so so on this is the intro slide, I suppose. And on the left-hand side, you're seeing the equipment I'm going to show you, which is this cloud chamber. And then on the right-hand side, there's a few typical snapshot images of some muons passing through the chamber. There's 4 of them. What you're looking at are these sort of, I suppose, ghostly streaks. That's the best way of describing them. Coming, passing vertically across the screen. Hopefully you can see that. I'm hoping the resolution of the Teams is going to be up to this. But so it's a little bit ghostly, but nevertheless, there they are. Okay, so moving on. So now I just come into the muons. What are they? The table I'm sure many of you recognise this. The table on the right is the atomic physics standard model of fundamental particles. So these are the particles that, as we know at the moment, as best we know at the moment, you can't break them down into anything more fundamental. So you've got the quarks at the top side, and for example, I think a proton is 2 up quarks and a down quark held together with I think it's a gluon, and a neutron is 2 downs and an up, something like that. So that's the top half, and the lower side of the table in green ones, these are leptons, and these are particles that don't really attach to anything else, so they exist on their own. An example of one of those examples, a very common one, is the electron. And alongside that, you've also got the muon is also a lepton. So okay. Now a muon is, as you can, I think, the mass is the top figure. I think that's the rest mass, isn't it? And you can see that a muon, for example, has about 200 times the mass of an electron. On the surface of the Earth, they're commonly found travelling at relativistic speed, so a very large fraction of the speed of light, so extremely fast. The rest half-life of about 2.2 microseconds. There are a few values banded around on the internet, but that sort of comes up quite a lot. And at sea level, commonly seen with very high energy levels, around 4 gigaelectron volts, and that's why they're of interest to the early scientists back in the 20s and 30s, because there wasn't much else around with that sort of energy level. The sea level flux, 1 square centimetre per minute. That's quite a lot, and again, that was really useful back in the day, because you've got a nice, steady, reliable supply of these things coming in, and of course they are unusually penetrative. So it takes quite a lot to stop them. Think of muon tomography, where muons are used to look through. I think the pyramids is a classic one, isn't it? They also used look inside volcanoes, tunnels, that sort of thing. And I think they're even used to look for look through containers, on import-export, passing through customs as well. I think I've seen that mentioned a few times. So very useful things. So where they come from? Well, cosmic rays, really. Cosmic rays, which are very, very high energy particles, collide with the Earth's upper atmosphere, and that produces a shower of secondary particles. Starting off with things called pions, but they have an extremely short half-life. I think it's something like 10 of the order of picoseconds. But so then they then decay down into muons and neutrinos, a few other things, and they're the particles that we see down on Earth. That's actually you may have heard of the muon paradox, which is quite an interesting thing, where if the muon's moving at approximate, very close to the speed of light, so 3 times 10 to the 8 meters per second, but the half-life is 2 times 10 to the minus 6 seconds, and if you try and work out, well, how far would a muon go in its half-life, so 3 times 10 to the 8 times 2 times 10 to the minus 6, you get 600 meters, and of course that's not enough to get from the upper atmosphere down to the surface of the Earth. And the common answer to that is special relativity, because the muons go, almost at the speed of light. Time for the muon is moving a lot slower than it is for us at rest, and so because the muon time is much longer, they do then have time to make it down to the Earth, to the surface of the Earth, which is, I suppose, quite useful for us. Okay, so that's the basics of them. Moving on to the history bit now. So, as I mentioned, mid-1930s, they were the prime source of high-energy particles, because there wasn't much else around. Cyclotrons were only developed in the mid-30s, and even then they weren't that powerful. So if you wanted for atomic physics research where you want to smash high-energy particles into something else and see what bits come off, muons were the source that was used. Of course, interestingly, the muon, of course, was only identified in 1936. So when you look at the early papers, certainly pre-36, the particles described as cosmic rays, because that's what they thought they were, and I suppose to some extent they are. These are the guys that identified them in 36, Seth Neddermeyer and Carl David Anderson. I particularly like Seth Neddermeyer's photo. Looks quite a good one. I think that was probably his security pass from Los Alamos, and he certainly looks quite a serious guy. As does Carl Anderson. Carl Anderson was very prolific in the early work. I think he discovered the positron using the sort of equipment we're going to talk about. So all good stuff. Now, how do you see? How might you see a muon? For your atomic research or just looking. So the way it's done is by using cloud chambers, and the sort of cloud chamber you may be familiar with is the diffusion chamber. And there's a little picture here on the left showing a few people peering into one, and lots of little tracks of what I think are alpha particles there. Amazing devices. Really, I've just been often described as one of the most magical pieces of scientific equipment you could build. They are absolutely incredible, beautiful to watch. Not that hard to build either. So yeah, something very, very interesting. But the sort of chamber that you commonly see around these days is called the diffusion chamber. And the way this works is in order to, of course, you can't see a muon. It's travelling far too small. It's travelling far too fast. So there's absolutely no way that you're going to see it directly. But as the muon passes through the atmosphere or a gas, it's knocking electrons off of the gas, of the atoms of the gas, and charging them up, ionising them. So it's leaving behind a trail of ionised gas. And if the volume that gas is in is saturated with something like for example, like alcohol, so it has a saturated vapour, which then becomes supersaturated. You then make supersaturated. So what you have then is the saturated gas is then wants to condense on something. But if you've made the vapour very clean and there's no dust in there or anything, it can't. It's just how it wants to condense, but it can't. A muon passes through, or an alpha particle or a beta particle, for example, leaves a trail of ionised gas behind it, and then the alcohol can grab onto that, condense onto it, and you can then see the alcohol droplets that are condensed onto the ionised trail. And that, of course, that's what you're seeing in the picture on the left. These are alpha particles that are running through there, leaving behind an ionised trail, and then the alcohol vapour that's in this chamber is condensing on those and allowing you to see it. Really nice, incredible things. But the problem for muons coming down from the upper atmosphere is that they're coming in vertically. And with this type of chamber, because gravity is necessarily forcing this supersaturated vapour to sit in a thin horizontal plane. It's typically, just a few millimetres thick, and absolutely horizontal because of gravity. So if you've got a particle coming down from above us, all you're going to see, in theory, is it's just a little dot as it passes through. You won't see much of a trail. So, which is a little bit awkward, really, when you're trying to look at muons. The great thing about them, though, is that it runs continuously. So these people here on the left are just watching. It just sits there, runs. Anything that passes through, you'll see it. But yeah, the drawback is not much good for things coming from above you. Having said that, I'm just going to break off a little bit here and show you a video. So, hang on a minute, before I do that, slideshow, current slide, yeah. So I built one of these back in the day. This was my diffusion chamber, which you're seeing here. These bits around it, these are some Geiger tubes, which I was playing around with at the time, trying to turn it into a coincidence chamber, which we'll talk about in a bit. But nevertheless, that was my chamber. So now I'm going to show you a bit of video, and I really hope you're going to see this. Hold on, sorry, not that one. So please shout out if you can see this. So, Andy, can you tell me, are you seeing...
I'm seeing the bubbly picture again.
Yeah,
with a white line through the middle.
Yeah, okay, right, okay, yeah. So this is looking down through the top of the cloud chamber. You're looking down onto the top of the cold plate. The black cold plate, it looks quite bubbly because at this point the chamber's been running for about an hour or so, and the alcohol vapour that's been sort of raining down and condensing on the cold plate. It's been forming these sort of droplets, really, and that's why it looks like that, because it's just alcohol building up on the surface of the cold plate. Now the band across the middle, this is actually a sheet of lead. So it's a 2mm sheet of lead, and it's 8mm high. So it's much taller than the supersaturated layer on the plate. So what I'm going to do now, I'm going to play this, and I'm really hoping you're going to be able to see the resolution is going to work, and you're going to be able to see this. So I'll play it, then I can use the slider bar to come backwards and forwards. Did you see something there?
Yeah, we did.
Okay, so I'm going to...
Yep, another one.
Slider bar.
Another one coming now.
Yeah, okay, so this is the same one, and I'm just playing it backwards and forwards so you can see it. Now, what I'm hoping you can see is there's a line that's running down here.
Yep.
Yep. So it's a straight line. It's gone through the lead plate. So this is a very high energy particle that can pierce 2mm of lead. And the other interesting thing is that coming off of the side here, you can see that it's knocked off a beta particle. See this wiggly line come off the side, and it's come off the lead.
Yeah, we can see that as well.
So whatever that was has knocked off a particle, has gone through the lead and knocked something off. Now, let's come back to the presentation. Let's find it. Yeah. So there's a thing called the...
Now, it was moving to the side because there is turbulence in the alcohol,
absolutely.
or what?
Yeah, it's not actually turbulent. So what's happening is that the vapour's coming down from the top. It's a bit like an upside down. Imagine a column of vapour coming down. It's got to go somewhere. So what it does, it goes off to the side. And so the reason it's moving slightly, isn't it? Maybe there's two things going on here. So the saturated vapour isn't constant, so the condensation's happening in a patchy form. So some bits will condense slightly earlier than others, even though the trail's there, because some bits of vapour are more likely to condense than others. That's one reason why you're seeing that. But the reason that the beta particle is moving downwards is because the column of sinking air is coming down, hitting the cold plate, then it's moving off to get out of the way. So that's why you're seeing it move. The beta particle certainly move off to move it down.
Well, wouldn't that be more like the closest example I can think of? It's more like a billiards game. You've got a high energy particle, and it might have been a muon that hit an atom, knocks off that beta particle, and it just goes off at an angle. It's just like on playing pool when you hit the rack, and then here comes an alpha particle off the side of it.
Absolutely, I think that's absolutely right. Yeah,
I think that's
why it went up. Interesting there that because the beta particle is quite light, they actually bounce off air molecules. So what happened down here was that it shot off. It probably hit an air molecule at this point and then bounced off to the side. So you get this wiggly line because they're not very high energy.
And it's very short, so it just got
very short,
there by the vapor, yeah.
Yeah, and then the little dot at the end, that's when it gave up everything it had.
Exactly,
when it stopped. Yeah.
It stopped, yeah. And it's charged, so you're gonna see the electrostatic effect on the isopropanol vapor. I guess that's what you're using, isopropanol, I assume.
Yes, isopropanol, yeah, that's right.
Okay, yeah, right.
Yeah. Okay. Yeah, good. All right, let's crack on. So that was the chamber. Might have been a muon. Went through 2 minutes of lead. Beta secondary. Now, the other thing is that there's this thing called the cos squared theta rule. So if muons are coming down from above you, then the rate if you're down at 45 degrees, say, then the muon rate's going to drop to the cos squared of 45. And if you get down to cos squared 90, then, well, cos of 90 is 0. So you shouldn't, in theory, you shouldn't really see muons travelling horizontally. But they've got such a long way to go from if they were generated off on the horizon, and we've got to make it through to where we are. It's quite hard. Nevertheless, I thought I'd show you that because, well, something happened there. All right, so that aside, so if diffusion chambers aren't ideal, there's an earlier type of cloud chamber called the expansion chamber. Now, this was invented by T. Wilson in 1911. And the way this works is rather than having a cold plate to supersaturate the alcohol vapor, what you have instead is in this volume here A, you have alcohol vapor. There's a separate volume below it, which is this area volume here. And if you have a vacuum chamber off to the side of it, if you suddenly connect the vacuum chamber to this volume down below, the piston gets sucked down, the pressure in the upper volume drops, and then its temperature also drops, and so this upper volume becomes supersaturated. And this was how it was done before the diffusion chamber. Now, the great advantage of this system is that it's not constrained by gravity. So this volume A can be any shape you like. That could be, rather than being a horizontal rectangle, it could be vertical, could be going up there. And so using this system, you can see particles coming down from the upper atmosphere much, much easier. But the disadvantage is that when you make this expansion, it's only sensitive for a fraction of a second, and it really is just a fraction of a second. So you fire this thing off, you see what was going on in the chamber at that time, and then it's all gone. So it's pros and cons, isn't it? You much better chance of seeing something, but that something has to have happened in the instant that you fired the chamber. I actually went up to Cambridge and I actually had a went up to see it in the Whipple Gallery, and I have to say I was actually a little bit disappointed in that when I got up there I found that this is my photo here. So it's actually just a facsimile of the device, not the original chamber, which was a bit disappointing. But never mind, it was better than nothing. Okay, so that was in 1911.
Yeah.
Now,
sorry, Dave. So forgive me, Dave. On that previous picture,
what the piston is.
Sorry.
So, sorry, I was asked the question. Why is there a battery connected on the side of it?
Ah, right. Okay, yeah. Okay, this is very important. So you've got all the time you've got things going, alphas, betas running through here all the time, and they're leaving ionized trails all the time. So you only want to see the ionized trail of the particle that has gone through the chamber at the time you triggered it. So you have to have a clearing voltage across here, so it's constantly clearing ions that have been formed during periods that you're not interested in. And if you don't do this, then you don't see much really. That applies to both types of chambers. You have to have a clearing voltage there to clear old ions, I suppose, clear them out of the way. That's a reason.
Now
Okay,
I've got
makes
two
sense.
questions then. A is the piston, and is it like the head of a drum?
In this early one, Ted, it was a flat plate, and it's got I think some walls running down here. Can you see there's like a liquid down at the base, down the bottom here?
Yeah, and so something slides.
Yeah, that's right. So there's this piston sliding down into the liquid, and the liquid's forming the airtight seal. But
very good.
in order for this,
now the battery Does that mean you have to disconnect it for the moment that you want to take a picture?
Well, yeah. Yeah. Very good point, Ted. Now, yes, you don't, for a diffusion chamber, you don't, because it's running continuously and it seems to work okay. For this expansion chamber, you do. And, well, I certainly do anyway, and it works better if you do disconnect it at that instant, because you don't want to, really be great if you didn't clear the ions away that you're actually interested in. So the trick is to fire the chamber, cut the voltage, and then see what happens.
Well,
and with my system, sorry?
As best as I can understand it, what happens is when you have the particles going through the chamber, they leave ionized nucleation points, and so those nucleation points remain there. And so if you don't clear them, what happens is it fogs up your cloud chamber, and then you won't be able to see the new tracks.
Precisely.
So you have to get rid of the pre-ionized nucleation site, so that essentially you have a clean vapor that you don't see any vapors in. So that's why you have to have that battery there.
I think that's right. Now I think it's less important in the diffusion chamber because that's being driven by gravity. The vapors
exactly. Yeah. More so in the Wilson chamber because it's momentary, right?
Yeah, and it doesn't have any other clearing mechanism.
Exactly. Yeah. Right. Exactly. Yeah.
Yeah.
So what's the battery connected to?
Okay, so that would be, in this instance, this would be connected to the piston and the top glass at the top. You just need a voltage across the.
Yeah, but
but
if you have a conductive metal plate under the glass, then you won't be able to see the tracks, will you?
No, but it just has to be a grid. It doesn't have to be a plate, Andy. It could just be a small grid, which is all I have.
Okay.
So you can see through it. It doesn't have to be a continuous plate. Just something of some form.
Ah, okay. And sorry, one last question. What is D?
Oh, that's a block of wood.
Oh.
So to stop the chamber, to stop the piston smashing into the ground and wrecking the thin tube that's sliding up and down into the water.
Ah.
I think the diagram is a little bit not quite right, but it gives you the principle. Because it's quite violent when this goes off. As you'll see with my system, it's quite violent. That chamber that piston really comes down quickly, and you want it to as well. Because it needs to be as instantaneous as possible. So you've got to accelerate that piston, which means it's got to be light as possible, accelerate it as fast as possible, but then you've got to stop it, and you don't want it bouncing back up again, because that will ruin things and cause turbulence. So it's a bit of a juggling act between speed and smoothness. Okay? Happy to move on, or still thinking about it?
No, please continue.
Okay. All right, so moving on now into the 20s. So for these atomic researchers, for the physicists at the time, so they're using muons coming down from above, and so they obviously turning the chamber around through 90 degrees, so that you've got your exposed volume is principally sensitive to things coming from above, which is what you're interested in. And you can probably see here the 30 centimetres. It's quite a big one, actually, this one, of the tube. Across here, this is a glass plate for viewing in. This is the volume that's got the alcohol vapour in. Now, on this one here, what you've now got is a rubber diaphragm, which is this part here. And that's dividing this forward chamber from the back chamber. It's got an adjustable stop, which you can see here, and that's being controlled by these little pistons here. And it has a dump valve in the middle here. And so what they're doing is pressurising the back chamber, which pushes this diaphragm forwards, slightly compressing the front chamber. And then when you want to trigger it, you open the dump valve. This pressurized gas escapes, and the diaphragm then flies back, and then because you've pre-filled this with alcohol, not filled, but because you've saturated this volume with alcohol, you then achieve the supersaturation in this volume here. And then if all goes well, then you might see a Muon trail like this one down here. But the big problem is, well, when do you trigger it? Because you don't know when the muons come through. And so what they were having to do was to just keep on triggering it. And every time you have to they had to take a photo. And you had to take hundreds and thousands of photos to get a good together before you got a good one. So it was a very inefficient process, which was slowing things right down. So the breakthrough came through in the early 30s by a chap called Patrick Blackett and Giovanni Occhialini, I hope I'm saying that right, at Cambridge in the Cavendish Laboratory. And they had the idea of the coincidence chamber, which I'll just come on to in the next slide. Here they are, by the way. That's Patrick Blackett. And if you go onto Wikipedia for Giuseppe Occhialini, this picture comes up. Now, do not believe this, because that doesn't look like a chap in the 1930s to me. This Blackett looks good, but I don't know what's going on here. They've somehow got the wrong picture. This picture down here, this shows them here. They do look like chaps from the 1930s. So this is Blackett, this is Occhialini. Incidentally, Blackett, he was Oppenheimer's tutor at Cambridge. He was the guy that Oppenheimer tried to, in the film anyway, tried to feed the poison apple to, because they didn't get on. But anyway, he was quite a character. Anyway, but this is a paper that they published in 1934, which shows quite a good cross-section of their device. And it's very similar to the last one in that you have a front chamber, which holds the alcohol vapour around here. It's got a moving piston, and then it has a back chamber, which has a dump valve fitted, this part E. And the big difference is they have a couple of Geiger tubes here. So these items C and C, and so they trigger when something goes through both Geigers at the same time. That's when they trigger it, and that made all the difference. So now you're only looking and taking the expensive photo when something's happened. This is on the Cambridge website. This is a photo that purports to be their equipment, but I have to say that as hard as I've looked at this, I can't really work out what's going on in here. If this really is it, or if I'm just not understanding it, or what, I don't know. But anyway, that's what it purports to be, the equipment. Lots of hundreds of little light switches everywhere, interestingly. But yeah. Now the way they and this is the dump valve, which is operating on a hair trigger, so quite a little complex little mechanism here. But the key is you want to evacuate this back chamber as quickly as possible in order to make the expansion as quick as possible. Now, what they were doing, they were filling the chamber that you're interested in. That's the viewing window, by the way, with oxygen to 1.7 bar, and then the back chamber was filled with air to 1.7 bar. So the piston is now balanced, and they could now control its position by just tweaking around this little light spring here. And then when both Geigers trigger, open the dump valve, off you go, get your expansion, take a picture, see if there's something there. The other interesting piece about this equipment is items D here, and these are big electromagnets, because what they're obviously to try and identify the particle. If it's got a charge, then if it's going through a magnetic field, then you might be able to bend it and then work out what the charge is. So Yeah, that's a section through their equipment.
Sorry, David. Before you move on, there, can I just ask? I'm probably missing something obvious here, but if muons are the particles travelling at near relativistic speeds,
yeah,
surely by the time this triggers from the Geiger counters, the particle will have long passed through the chamber and moved on to.
Yes, it will.
So how is it still able to pick it up?
Okay, yeah, absolutely. You're absolutely right, Andy. It will be long gone, but the trail of ionised gas it leaves behind will still be lingering, and that's what you're looking at. It's not the muon; it's the ionised trail, and the ionised trail takes time to dissipate.
The other thing, I guess this must be a key of how much the volume changes, because the ionised gas will be in a smaller volume than the volume that you get by the time the picture is taken when it's expanded.
Yep.
Is there much difference in those two volumes, or?
It's okay. So you might better get a feel for it. In that diagram, it's looking like, what have you got there? So on that scale, have you got 4 centimetres there? You might have a centimetre at the back there.
Mm-hmm.
So maybe it's a 5 to 4 expansion, 4 to 5 expansion, and yes, it will distort the tracks. Absolutely, it will. And the one of the big problems with this type of equipment is minimising that distortion, because you've got distortion from all kinds of sources. You've got turbulence, which is the big one. You've got gravity, which is going to be pulling the ionised trail down, and then yes, you've got that stretching motion of the expansion. So they're all working against you, and you've got to try and do the best you can against those drawbacks. But nevertheless, that's what they were doing.
And most importantly, you still see the track.
Yeah, you do. Absolutely. And in this next slide here, you can see this is some examples. This is from Blackett's paper, and showing some of the tracks he's getting, which pretty amazing. And I haven't got anywhere near close to this, but you can see some of the tracks are circular. That's because the magnetic field that they're running through. Some are running straight down. That looks like an alpha particle down here, big one. But lots of things going on, and this is when they were able to start making some big advances once they got this system up and running. Now, an interesting thing then is to say, well, right, well, what happens if you make these muons go through something? So a plate of lead, for example. And then what happens then is the muon will start smashing into the lead atoms, knocking secondaries off, and that's when it all does start to get really interesting. And you can see some of those photos in the images on this screen.
So those circular patterns are most likely beta.
They may well be, or maybe something else. I don't know. But
you only have two choices: betas or protons, and besides the muon being electrically negatively charged, but it's so high energy you don't really see the curvature.
Yeah, if you interestingly, if you look at, I don't know if you look at this is an extract from Blackett's paper. So in figure 16, he's talking about tau mesons being developed.
Oh gosh!
Which have got a positive charge.
Oh no! They actually seen taus. That's well. I mean, the lifetime of a tau is like infinitesimally small, even compared to the lifetime of a muon.
But
so
maybe he's wrong. He's claiming
it could be, but I mean, if you look up the lifetimes of the tau, I mean, it would only travel like millimeters before it decays.
I have to say I didn't worry about that because I haven't got anywhere close to this. I'm just happy to see a track. So and I also haven't got any massive, huge magnets massive electromagnets to do this either. So
I
don't know.
find yourself an old surplus magnetron.
Yeah.
And use the magnets off of it. Go to. I mean, those are huge magnets, that wrap around the magnetron, and those are perfect. If you can just place them across your chamber there.
Well, last year I was fitted with a pacemaker, so I'm not so sure I want to do that. But
okay. Well, I apologize then. Sorry, it's maybe not such a great idea then.
I would like to have done, but yeah. Who knows? Maybe one day. But for me, just getting to the state, getting a track. That's what I was trying to do. All right. So I looked at this and I thought, my thoughts were, how hard can it be? It doesn't look that hard, does it? So maybe I can have a go at doing this. And so I've started to try and I've called it an imitation. I'm not going to go anywhere near as far as saying it's a replica. Just, can I do something? And this is after several iterations, a few years actually. This is what I've come up with. So, and it's a bit of a hybrid between the Blackett and the Wilson type, because I've got the front chamber. This is the chamber holding the alcohol vapor. I've got the back chamber. This is the chamber that's going to be expanded, and there's a diaphragm between the two, and that's the diaphragm as the back chamber gets evacuated, the diaphragm moves back and it then drops the pressure in the front chamber, hopefully supersaturating the alcohol. You can look at what's going on through a viewing window. But I wasn't too happy about. I don't have a reliable source of oxygen at 1.7 bar, and I was a little bit worried actually about doing that with a glass, looking through a glass window with 1.7 bar behind it. So I've used more of the Wilson system, where you have a vacuum chamber at the back, and then when I've got 3 Geigers, incidentally, to sort of cut down my false positive rate. And then when they trigger, I've got a solenoid valve here, which is not as good as Blackett's by any means, but it's the best I could do without spending huge amounts of money. So I've got it, so the Geiger's trigger, solenoid valve opens, exposes the back chamber to vacuum, sucks the diaphragm back, and depressurizes the front chamber. And this is just a quick animation of how this is working. So this is when everything's armed. So the solenoid valve is closed. The back chamber's got a slight positive pressure on it, about 100 millibars, which pushes the diaphragm forward, which slightly pressurizes the front chamber. Incidentally, that frame there, that's my high voltage frame, just to put a bit of a charge onto that. This chamber's got a glass wall, and then around it there's a plastic tube with these are lights, LED lights around the outside. So the frame's at about 200 volts, and this back grid here, this is grounded, so that gives me my voltage across the chamber. Back chamber solenoid valve. So when it operates, there we go. So the red line is a muon coming through. I'll just flick this back and forwards so you can see this is armed. Muon comes through, solenoid valve opens, diaphragm flies back, and depressurizes the front chamber, supersaturates the alcohol vapor, and then hopefully, if all's well, any ionised trails are revealed, and you can take a picture through the window. So that's how it works. Oh, yeah. So you might be thinking, oh, this is all very complicated, isn't it? I'm not sure I can do this. But there are, on YouTube, there's loads of YouTubes for building diffusion chambers, but there are one or two where people have built expansion chambers, and this I quite like this one. This chap called Marb's Lab, and he's built an expansion chamber just using hand tools. So I just thought I'd put that out to people if anyone was interested, but they didn't fancy all the machining. That's always not lost. Can be done to some degree anyway. All right. So for my Geigers, so what did I do? Well, I didn't know about scintillation plates at this point, but I knew about Geiger monotubes, and I got this Keijo system which you can get on AliExpress and eBay, and actually quite cheap actually. It's got a little Chinese tube in it, and so I started off using that. They work really nicely, and I think they're something like £15, something like that. Nothing very cheap. And in the early days, I did a bit of muon counting with these. I stacked two on top of each other, and then I built a little logic gate with an AND gate there to look for the coincidences. And then when I got something, I fed it into an Arduino, which then logged it using a real-time clock on SD card. So that was quite interesting. And I could play around with this, vary the spacing between them, vary the angle, and look to see what happened. And I started off using that, but then I found these are quite small. These are 1 centimetre squares here, so that's what 1, 2, 3, 4, about 6 centimetres across, and only about 1 centimetre wide, so quite small. But then I found these SI2G tubes. They're sort of Russian in the 70s and 80s, which at the time you could get from Ukraine. Again, not too expensive, but I'm not so sure you can still get these now. But anyway, I switched over to these because they give you much more volume. So, and they work just as well on the Keijo board. So I was using those, and then to do the final control, I've got 3 Geiger tubes, and I've fed them first into a logic board. So this isn't got an AND gate chip on it. There's 3 555 one-shot monostables just to condition the signal, and then I feed that through into an Arduino, and the Arduino then does everything else. So it then, once it sees the ping from the AND gate, it fires the solenoid. It cuts the high voltage, and then it does it automatically resets everything. So I've got this set up so it runs automatically. I don't have to do anything. I can just fire it all up and then wander off and let it do its stuff. And then just to finish this bit off. So when these expansions happen, it's very fast, and on average about every 2 minutes, something like that. And you get bored, to stand looking at this, looking into that window for 2 minutes. Sometimes it's 10 minutes between expansions, and I can't concentrate that long enough. And even when it happens, you're not even sure what did I see. I can't remember. So I have a video camera recording continuously, and ideally in complete darkness to cut down reflections. And then I let it run for 20 minutes, an hour or so, and then when that's all over, I can then download the video and go through and look at it, look at the expansions carefully and see if I've caught anything. Hopefully, there's something every 4 to 5 expansions. I think Blackett was claiming 80% hit rate, and I haven't got anything near that. 20%, 15%, 10%, maybe something like that. But so I've got a way to go. But anyway, that's how I do it. So now that might be a little bit difficult.
You have a video camera, but you don't have to watch the whole 20 minutes. You know where to look for?
No, because you hear the bang. So when it fires off,
bang. Ah, okay.
You get a bang. So I use DaVinci Resolve, and I just look for it, and I look for the noise spikes when it makes the bang. Yeah, I wouldn't want to sit there looking at the whole thing. And so I cut those out, identify them, then I can look at them in detail. yeah, so that's how it's done. All right, so there we go. So what I do now I'm going to stop sharing now. Now I'm going to try and do the chamber tour now. So I'm going to now switch cameras. So bear with me for this bit. Right. I still need to share my screen. Andy and I practiced this bit a few times, but I'm bound to mess it up still. Okay. So what are you seeing now?
At the moment, we're still seeing all the different faces of everybody. The gallery.
Maybe I'll have to go onto Zoom then, and
I think you need to share your screen first, don't you?
flip cameras.
Yeah. But
Absolutely.
have you done share screen in Teams yet?
Yeah, I'm just trying to do that now. Entire screen. Allow. Okay. What are you seeing now?
Still got the gallery
Just
at
you
the
guys?
moment.
I haven't clicked allow. I'll click allow. Try that.
Ah, yes, brilliant.
There we go. All right.
Yep, there
so
we
what
are.
I'll do now, I'm going to switch the lights off now, and
we can see your video camera that's pointed at the cloud chamber at the moment.
Yeah, that's the plan. So I'm going to fiddle around with lights now. So you can, and I'm going to just try and give you a bit of a tour. I think if I turn on the cloud chamber lights. I'm going to try turning off the back. No, I don't want to do that. I'm just going to fiddle around with this. Try that. Try the other one. Just trying to get the best combination. That's not too bad, is it? So, all right. So what you're seeing at the moment. So this is the viewing window, effectively. The two squares, the diamond, I suppose, and the square in the middle. This is a little wire frame sitting inside the chamber. That's the positive end of the high voltage screen. You can see the upper and lower Geigers. I'll try and spin round here a little bit.
Yeah. So it's worth saying, Dave, that there seems to be relatively poor contrast on your video camera. We can see it.
Yeah, but it's pretty rubbish, isn't it? So apologies for this.
No, I don't need to apologise.
Let's try changing lights. Any better?
I think it's a little bit better.
Maybe slightly. Yeah, I've just got a cheapo webcam on it.
Fair enough.
It's probably a mistake.
But we can see your chamber, though.
Yeah, all right, okay. So I'm spinning this round a little bit now. So now you can see. Let's see how far we can go. I'll show you the essential elements. So this get me pointing still. Don't get in the way. So this is the front chamber, running back to the diaphragm lives about here. This is the obviously that's the lighting ring, and then move this out of the way. You can see the GM tubes. This one here, and here. They're in a plane with the lighting ring. So that's giving me you can get a feel there for what my sensitive viewing plane is running down through the chamber. It's about in this plane, the viewing plane is about 7 degrees wide. So if you think of it as a Muon telescope, 7-degree Muon telescope. But in this plane, it's more like 60 degrees, that I can see. Spin it round a little bit more. All the way around. Pulling anything out.
We
So
spoke of applying the vacuum. We spoke of applying the vacuum, but you haven't spoken how you recharge the thing.
Oh, okay. So the vacuum chamber runs all the time, and the pressurization works all the time too. But I run it through some throttle valves. So the expansion volume is much more than the vacuum pump running through the throttle valves can sustain. So when you fire it, it takes the vacuum pump, I don't know, 30 seconds or so to recharge the vacuum tubes. The vacuum chambers. And that's just done with some throttle valves which are over the back here. Just see the top of one there. So that's the valve. There we go. That's the pump valve. And this so let's see. That's the vacuum chamber. That's a little blow-off valve for the vacuum, so I can control it. And then down the back here, that's a pressure relief valve, so I can control the pressure that's being supplied to the main chamber. Well, again, you can see the restriction. There it is. The restriction valves here, which are limiting the amount of gas. The two pumps, which are down here, the vacuum pump and the pressure pump. They're limited by the vacuum pump. So spin that round. Oh yeah, that's the high voltage supply. It's just one of these eBay these buck converters. I think you get about 1,000 volts at that normally, but I don't use that. Okay, so let's show you the control boards now. I'm going to extend my fire that up, and you can see the name. Sorry about all the jerky pictures. Right. So I'm going to fire up the tubes and the boards now. So let's switch that on. So hopefully you can hear some clicking going on now. Right. So the input from the Geiger tubes is coming down these three cables here. They've got three of them, so I've got three 3555 monostables to condition the signal. And that really turns it into a square wave and inverts it so that the AND gate can seal nicely. And then once that's detected something, it then runs off into the Arduino. This is a little board here just so I can control it manually, so I can make manual fires. And this board at the back here, this is controlled by the Arduino, and this is just a whole bunch of MOSFETs that control the power to the solenoid, power to the HT, and using all that, the Arduino, once something's fired, waits a bit, then it resets everything automatically. So, and then you can see a little counting just so I can see how many times it's fired. All right, so that's the tour of the equipment. So what I'm going to try and do now is to show you it running. Now I need to do a little bit of expectation management here.
Can I ask a question?
Yeah, please do.
So you've got three Geiger counters, and you're running them, through is that a triple input AND gate in order to get not coincidence but a triple coincidence?
Absolutely right. Yeah.
Oh wow! Okay, great, fantastic. Oh, that's really neat.
I sort of cut down the probability of a false signal.
Oh, absolutely. That's just wonderful.
Yeah. One thing I would say is that as you see, the resolution of this webcam I'm using for this is absolutely awful, isn't it? It's not really focusing very well at all. What has happened while we've been talking, because I've pre-charged the chamber with alcohol. What's happened while we've been talking is that the screen is completely plugged out with alcohol. So I've got a hairdryer here, and I'm going to play the hairdryer on the screen just to try and get some of this fogging off. So apologies for this, because it might get a bit noisy when I do. Right, so I've had to do quite a lot of warming there, which is not great. That's going to muck the thermal equilibrium up a little bit. But nevertheless, still we have to do. So a bit of expectation management here. So in order to get this up and running, there's normally a period of running and settling and getting everything about half an hour to get everything settled down and stable. And I don't have that within the confines of this meeting, so they just have to do the best we can, really, and at least it'll give you a flavour of how this works. But never mind. If we don't see anything, then I've got some videos of things I have seen. Right. Okay. So let's turn some lights off. Hopefully I'll get rid of some of the background. And the focusing is still awful, but never mind. Right, okay, so what I'm now going to fire up the pumps and the vacuum. Right, so probably hear sort of a lot of thumping going on. That's the pumps running. So I've got this gauge up the top here. This is the chamber pressure, and there's another one up the top here, which is the vacuum, which you can't see because it's just too dark, isn't it? So if all three Geigers trigger, then it will make an expansion. Now, we shall see what happens. And what if we're extremely lucky, you might see a trail running across vertically down the chamber. I'd say that's probably going to be extremely lucky. I haven't been able to do any of the any of the pre-setup with this. The other issue for a demo is that the mean time between expansions is about 2 minutes. So sometimes it can be might be 5 minutes, might be 10 minutes, and then it might go 2 or 3 times in a minute. And because we're in a demo, almost certainly it ain't gonna fire. So just bear with this for a bit till you've had enough. And yeah. How are we doing for time? Because I've completely lost track of time.
Yeah, I'm sure everyone's enjoying this presentation, Dave, so don't worry about it.
I know, we're going for over an hour, haven't we?
It doesn't matter.
Apologies for this.
So can I ask that further question on your circuit there? So
please do.
Your AND gate then feeds into the 3 AAA bistables, and then so the trigger input. So then when the AND gate fires from all 3 inputs is when you trigger the I'm sorry, the inputs go first to the 555 IC.
Yeah,
and then
that's right.
And then they square wave the input that then feeds into the AND gate.
Yes, that's correct.
Okay, and so then the AND gate then just has the downstream amplification for your expansion valve and so forth.
Yeah, that's exactly that. Yeah.
Okay, got it. Great, fantastic.
Yeah.
Right, is there anybody else that would like to make any comments or ask any questions from David here?
I think of 2 Geiger tubes. Where's the third? Are 2 of them at the top?
Yep. Okay. So there are. It's going to fire, isn't it? As soon as I move the camera. I'll turn the light on. We'll just risk it. So two tubes here, Ted. At the top, one there, and then the third tube is down the bottom here. So they're spanning the chain. But I'm asking all 3 to go simultaneously.
And why is 3 better than 2? Just more confidence?
Well, yeah, maybe not, Ted. I mean, I just thought, well, because I'm putting a square. My pulse is, I think, is 600 nanoseconds, I think, and I was just worried that with 2, I might get a beta in the top and a beta in the bottom, and it just triggers it off. And I thought, well, if I got 3, then much less chance of that happening. Wouldn't be a problem, I suppose, anyway, because all I'll do is it'll just fire and there'll be nothing there. Doesn't matter really, does it?
Absolutely, yeah.
I think you just had 3 tubes. Okay, this is good.
Yeah, and I've got lots of them, so I thought, well, why not use them?
Well, the response time of the circuitry leads you to a statistical non-muon firing 2 tubes at a time, just from random radiation. Much reduced from a single tube, but still significant. But for that statistic to go random 3 tubes firing within the dwell time of the circuitry is just vastly less. So you've got to have that muon going through all 3 tubes to really bring down the statistics of random firing that would give you a false coincidence. So I don't know if that makes any sense, but that's the way I see it.
That was my thinking too.
I'm back to a physics question. The muon is traveling through the chamber. It is disturbing, I guess, the molecules along the way, ionizing them slightly, and therefore the muon is slowly losing energy by bumping into things.
Not even.
Somebody's
I suppose it is. I suppose it is, but it has so much energy that I think, my understanding, it makes almost no difference to it at all.
It's like a bullet going through tissue paper.
Yeah, okay, that's what I'm thinking, yeah. But we see the effect of the tissue papers, yeah.
You see the shredding, in other words, the ionization of the molecules along its strip.
So I've just for your reference, guys, I've just had a fire, but the chamber didn't trigger. It's probably something demo.
No.
Okay, I've reset. I should be okay now. So, pattern. Well, I'm charged up, so it should be. The count's still on 0, so maybe not.
I'm thinking of the hours you sat here watching it just like this in the beginning.
Well, I that's why I've got the camera tagged. So I get this up, satisfy myself everything's working right. Then I wander off, and I come back 20 minutes later, and I look at the Muon counter and think, oh, there we go, there was one. So that was a fire. I don't know if you saw anything.
We could see the meters move around too.
Yeah, I don't know if you saw anything in the chamber.
And some pumping, yeah.
I don't know if you saw anything in the chamber. I have to say I certainly didn't. When I do this, I use my phone to do this. It's a much higher resolution image. This webcam's not at all ideal, but nevertheless, you probably should still see something. I'll give it a bit longer, and then when you've had enough, I'll stop this and I'll show you some that I took pictures that I took earlier. But I think that you probably saw the auto function going on there, so it did the fire and then reset itself. But so at least I hope it gives a flavour for how this is working. But yeah, you tend to zone it. If you're looking in the script. Oh, there's another one. And there was something in the middle there. I don't think it was a Muon. Might have been a beta or small beta or something. Just below the LED screens. Don't know. That would be one where I would go back and look at the video, and with the video I can run it all at 1/10 speed and look much closer to see what it was. I'm actually going to increase the pressure a little bit because there wasn't too much. So I've just increased the chamber pressure by 10 millibars, which should make it a little bit more sensitive. Either that or it'll fog the whole thing out. This is where I went to get to black. Try to get to black, it's 80%. So how on earth you manage that, I just don't know. The voltage. I've got a bad earth, haven't I? Well, okay, that was disappointing because I think it looks like I've got a bad earth. I don't know if you saw some trails, there was something going on in there. How did the lights fade out? Bad connection somewhere. It's demo mode. I'll give it one more, and then I'll stop it, and I'll show you some examples, ones that I made earlier. I actually stopped doing this back in April last year when I discovered radio astronomy. So I was doing this for some years. Then bit of fog in there. Okay. So this hasn't run for a while. But all right, what I'll do. That second one happened too quick before everything had recharged. Well, I think what I'll do, I'll stop it there, as you've seen it run, and I'll show you some examples of what I've seen.
Now
I have another question.
You have a little
Yeah.
bit of lead in the middle. It's kind of like a shelf, but it's not rectangular. It's got a little notch in the middle of it.
Okay, yeah, all right, I'll show you that first. Okay, what I'll do, I'll switch it off, and then I'll put the lights on. You'll be able to see that in a bit more detail, what's going on, and I'll explain why.
And I have a quick question. What percent
Yeah.
isopropanol do you use to charge the chamber with?
Okay, so I've got 99% isopropanol, but I'm using it in a 60%, 40% water ratio, which is the ratio that was generally recommended by in the papers. They all talk about 60-40. It's working nicely. For a diffusion chamber, I use 100%, but for this I use 60-40, and it does seem to work better.
I see. So does the water help to what, the ionization or
I don't know. All I was
Okay.
doing was copying.
Okay, yeah, I'm just curious about that. All right.
So one major problem with this is turbulence. You have to get the alcohol vapor needs to be uniform across the chamber. I'm not seeing my finger on. So up at the top, there's a pad. See that pad there? That's got the alcohol. So the alcohol vapor rains down to the bottom. Now, if you have a lead screen that runs all the way across, then the concentration of alcohol at the top is going to be higher than it is at the bottom. So, for that reason, you see the lead sheets there? I've minimised them so that to allow the vapour to get equalised between top and bottom chambers, and also to minimise the amount of turbulence that happens as the diaphragm flies back.
Oh.
So I'm saying that when I'm looking for things going through the lead, I'm only then interested in bits that actually contact it. And I've got some video that shows that. Not many.
Because I'm thinking that isopropanol is a fairly neutral molecule, and
Yeah.
but water obviously can ionize more readily. So that's why I was thinking that perhaps the water would help in the ionization.
Okay, that's interesting.
It's hard to ionize isopropanol. It's a neutral, organic molecule
Yeah.
that doesn't really have a charge
Yeah.
on it. But you can easily dissociate water with an electrical charge. So that might help in the ionization. Is what I'm currently thinking.
Good point. Yeah, I mean, certainly pure alcohol works in the diffusion one, but all the old boys, they all talk about 60-40, and those who knew what they were doing. So, yeah. Anyway, yeah. The other problem with putting the lead in is because this is because as you expand it, the lead disrupts the condensation of the alcohol around it. So I think you see that lead I've got there is very thin, and the lead in the paper, in Blackett's papers, is something like 6 millimeters thick. It's huge. But that thermal mass, in my experience, just slightly warms the gas around the lead, the air around the lead, and stops the condensation happening. And I found this I get the much better results without the lead in than with the lead in. But of course, the one with the lead in is the most interesting one. So anyway, yeah, there we go. So that's a little bit about what's going on with the lead. I'll stop the camera now. See if we can get back.
It'd be interesting if you could substitute a different element, like either lithium or maybe thorium or something else, or you might see some interesting nuclear effects from the muons going through it.
Yeah, yeah. Good point. Yeah, yep. Okay, I'll stop. I'm going to stop the camera now. What are you guys seeing? Can you see video now?
We're back to a picture showing a bubbly screen with a white line, curved line through the middle of it.
Yeah, perfect, Andy. All right, okay. That's the first video I showed. So what I'm going to do now, I'm going to show you a couple of other videos. So I'm going to show you this one here.
Yep, that's running.
Right. Okay. So let's show you that. Again, it's almost looking at ghosts with this. So, but I'm hoping that you can see down the middle.
There's a line going through it.
A line down there. Yeah, that's exactly. Let's go forward. That was full speed, and then this is slow. So I'm just slowly running up and down. So there you go. There's another one. So here's one going from sort of 11 o'clock down to 5 o'clock. Yeah, it's quite tricky doing this with the turbulence and the. Well, let's show you another one.
You see some blotches as well as the lines. Are the blotches particles as well?
Okay, so this is a slightly better one. Let's come back to that. So there you go. Here you go. There's one running down through there, and then there's another one. Another one. Yeah, the blotches, Andy. So what are those? Don't know. Something. Maybe it was a. I don't know. Maybe it was a beta. Maybe it was an alpha. Maybe it was running. Just happened to be going by. You occasionally get these like increases in brightness, which I might be variations in the alcohol vapor, local ones. Perhaps. See, the sharpness I get is nothing like. Oh, that's the same one, just slowed down. Okay, no lead.
It seems your positive plate was in a different place at this time.
Yeah, it probably was, Ted. I mean, these have been done over. I've taken these examples over. They're all different voltages, different pressures. Okay, so look at this one here. Look, two of them. I'm moving the slider bar up and down, which you may not be able to see. So the two parallel ones there. They're quite nice and sharp too, these ones. I was really pleased when I got that one. So there we go. So this is with no lead, and this is with no lead. It's much easier. But I'll show you some now with some lead. So you can see the two lead strips. We're only really interested in anything that's going through one of those two. And you can see there's a line here coming from here down there, and it's going through the lead. But you can see how when you get near the lead, it's pretty rubbish. And this is a problem that I still haven't got round. How do you stop the lead disrupting everything? I think this is the same. This is the same thing, just running slower. And then this is the last one I'm going to show you, which I think it's one of the most interesting ones. So I'm going to run this. Let's come back a little bit. So I'm fine. Just the right spot here. So look at this. There's a little shadow up here of something up the top, but after it's gone through the lead, it's split into two. maybe I'll go to the 1/10 speed. Or anyway, I've convinced myself it's split into two.
Oh no, it's 2.
Yes. Yeah. All right. Okay. So there we go. That's it, guys. I've probably gone on for long enough, haven't I?
Wow.
I'll stop it there.
I think
Now,
that was
again,
pretty
on the last
amazing.
video, you had your positive anode, that nice big diamond on the front. How did that improve things?
Yes, it made an improvement in sharpness. Ted. To begin with, my anode was just the lighting ring around the top. Let me. Have I got any pictures of? Before I had that in there, I was just relying on the clamp ring that's clamping the glass to be my anode. And I put the grid in later to try and improve things. I was trying to imagine the shape of the electric field, and how uniform is the field? Because obviously you want a nice uniform field. And I thought, well, if my anode's just a ring round the edge, then maybe it won't be that good in the middle. So I put the grid in, but of course you still need to see through it. So that's why it's a grid, not a plane.
And I have another question.
Yeah.
Did you ever try just placing a radioactive source in
I
any
do.
of the chambers, just to see a big shower of stuff?
Yeah, I have, and in fact there is one in there. There's a bit of americium in there, which I use for setup sometimes. It's screened off at the moment because you don't want it to affect anything. But yeah, there's a little bit of americium from a smoke detector. With it, I've got it. It's covered up at the moment, so.
And that's handy.
Yeah, that's right. And it just shows you that the alcohol concentration's about right before you waste your time. So there we go. Any other cues? I'm very conscious that I've massively overrun here.
I thought that was very interesting. I'm most impressed with what you've done.
Thank you.
I have one suggestion though, and that is to improve the contrast of what you're seeing. It looks like the inside of the cylindrical pieces is quite polished and reflecting the light.
Yeah. Okay. So. Very good. Yeah, this has been another problem. So, the inside of the cylindrical piece is actually a glass tube, and so it's very shiny. But to begin, some of the early ones I had an aluminium tube, and of course that was rubbish because my electric field was hopeless because of that. And then I had a plastic tube. That wasn't very good because the alcohol vapor didn't like the plastic. So I then went to the glass tube, and that improved things enormously. It's nice and smooth. It's not going to disrupt the gas. It's electrically insulating, so it splits the anode and cathode up nicely. But yeah, a problem is contrast, and you also the glass. You need the lighting ring to be able to see things, but you don't want the light reflecting off the front. The glass viewing window, and you don't want it illuminating the felt pad on the back. And how do you constrain the light to just a thin band? And that's been quite a problem I've been working on.
Could you just use black card and fold that and tuck it in there with holes, of course, for the lights?
Yeah, quite possibly, John. Yeah, and that's a good suggestion. Yep. Could well do. Or even spraying it maybe with something that's alcohol resistant.
Yeah, or they sell some felt for going inside telescope tubes. Maybe
okay, yeah. That's an interesting idea.
Okay, well, thank you very much indeed. That was quite brilliant, Dave. I think we should all give them a bit of a clap.
Thank you.
Thank you very much indeed. Wow, brilliant. Well, it's now 25 to 10, so we go for about an hour and a half. But I mean, that was quite a fantastic talk for that hour and a half. I have something to present for around about 5 minutes or so, with something a bit hot off the press. I don't know whether anybody else has anything that they particularly want to talk about. Is there anybody else? No, nobody at all.
Dave, I think we're having audio problems. Do you have a mic and speaker both together?
Oh, am I feeding back?
Thanks.
I'll try and plug this. Okay, I've just unplugged the
presentation.
Yeah. Well, I'll just mute. I'll just
mute.
mute you, Dave. It's okay. I'll just mute you.
I've oh, okay.
Yeah.
I've
I've just muted everybody. Okay. So I'll just show what it is that I was going to present. Need to pull it up. Just need to share my screen. Right, having muted everybody, could somebody just unmute themselves for a second and just let me know whether they can see a thing that says BAA online Muon detection meeting?
We see your green screen.
Yeah, thank you. It's only about 4 or 5 slides, so it won't take very long. So just start off with something that I presented yesterday at the SARA meeting, the Drake's Lounge yesterday, and then some hot off the press extra bit of research I've done today. So I know that UK RAA are now producing pico muons, but this is still using 2 of the UK RAA's Cosmic Watch muon detectors in coincidence mode, which I've misspelt. No, I haven't. I spelled it correctly, sorry. And what I presented yesterday was an experiment that I'd done where I put various amounts of lead between the 2 detectors and to see what effect that had on the detection of muons by the detectors. So here's an example. I had some of this roofing lead, which I've sort of folded over into various pieces. So I had from 0 to 5 between the 2 detectors. And the thing to bear in mind is that each time I put the lead in, an extra piece in, it doesn't just put extra lead between the 2 detectors, it also actually stretches the distance between the 2 detectors, which wasn't something that I thought about too much at the time. And this was the results that I presented yesterday at SARA. This is just exactly the same graph, but in 2 different sort of colour schemes of it, because I didn't know which one was going to be easier for you to see. And you can see there seems to be quite a profound change in the detection rates as the lead increases in amount, from 0 sheets at 0.65 counts per centimetre squared per minute, down to at 5 sheets 0.1 counts per centimetre squared per minute. And I've demonstrated at the end that when I took the lead away, it went back to the baseline again. And we had a discussion about this yesterday, and it was noted that this seemed to be a very large amount of reduction for muons. So the following bit here comes from ChatGTP, because I don't claim any particular level of knowledge on these things. But this is the real question: were these type of results fitting in with the characteristics of muons at ground level? And the real issue is that muons do not behave in the same way as gamma rays or beta rays or beta particles or alpha particles, and then so you wouldn't expect an exponential reduction, which is what we seem to be seeing in that graph above. I don't even claim to understand the calculations here, but this is what ChatGTP came up with. And the bottom line is that a few centimetres of lead, you would expect almost no... Sorry, got some feedback from somebody there. As some,
I was just I was just going to say, Andrew, have you considered the Muon telescope effect? So as you're putting the lead in and you're moving the scintillators apart, you're effectively decreasing the viewing angle.
right. Hold that in your head, because it becomes relevant in a second. Okay. So as I say, we wouldn't expect much attenuation with a few centimetres of lead. So there was a couple of experiments were recommended yesterday to take this a bit further. One was to do the same experiment, but this time rather than using lead, to effectively just use air, something as an alternative spacer that doesn't really provide any particular density. And the second thing was I think Adrian came up with this particular one, was try and keep the detectors at the same distance from each other and then put different amounts of lead between them. Today I've been able to do the first one, which is really where you're coming from there, Dave, really. So hot off the press are my results, which is what I want to just present this evening. And I don't know how easily that purple shows up on your screen, but the bottom line is that I seem to have virtually replicated the same results just using air. And what I've done here is I've tried to put the two sets of results together, and you can see it's almost exactly the same as each other. So it appears that the lead has made no difference at all. It is indeed, as you say, the Muon telescope effect of just increasing the distance between the two detectors that's led to this apparently quite large reduction in detection rates. So that's all I wanted to present tonight.
You
Now,
can
the
actually
telescope
model that.
effect is simply a probability math, then?
No.
As I understand
You
it,
can
it's to do
calculate
with,
the telescope effect with a bit of computation. It's purely geometrical, and if the amount of attenuation you see as you increase the distance between the two detectors follows the model, then you've nailed it.
Well,
And that's just because it's unlikely that a muon is coming from that particular angle to fire both. Is that right?
Yes. Yeah, that's it.
I suppose if you're looking more or less vertically, the number of muons coming down is more or less constant. It's only when you go to larger angles in the cos squared formulation that you get significant reduction. So the telescope effect would be quite easy to calculate, I think. Perhaps not at this time of night.
No, that's exactly right. I mean, you're viewing at a smaller angle of the muon passage as to the probability that it would go from that angle through both detectors, and so when they're close together, you have a much wider angle of acceptance into the detectors, and so you get a higher count. So it's absolutely the telescope effect.
I'm just wondering to see if I can get a quick determination. So if I ask,
I think calling it the telescope effect isn't exactly right. Maybe more collimation effect or camera obscura effect, something like that. Shadowing effect.
You're not shadowing. These muons, if they can pass through lead, you can't shadow them.
No, shadow is the wrong term.
Yeah, it's the angle of essentially a muon having the essentially the passage through both detectors simultaneously. As you separate them, the angle becomes narrower, and you're only seeing the muons that are going through that acceptance angle.
Yeah, that's right.
And so the further apart they are, well, the narrower the angle, and the narrower sort of volume of space that you're essentially analyzing for muon showers. So anyway, but it'd be interesting to see if now with that separation, Andrew, and you did place those massive amounts of lead thickness through it, if you saw any attenuation at all. That would be kind of an interesting experiment.
I mean, certainly it. the results on my graphs there don't really seem to show any significant difference.
Yeah,
And we see,
probably not much.
I mean, I do intend to do the second one that you mentioned, trying to keep the distance the same, and then put different amounts of lead between them. To need to find an appropriate box that will sit in there and do it. But
Probably wouldn't
It would-
see too much, but yeah.
But it would probably be easier if you have 4 detectors. So 2 with lead and 2 without. Because otherwise you also get the statistics of the muons entering the detectors anyway. So maybe, well, if you don't have 4, of course you cannot do it. But if you have 4, you can have one setup with lead and the other one next to it without.
yeah, unfortunately, I don't have 4. Have you got 4? Maybe you could do it for us.
No, I've got the parts for 4, but I still have to build them. So.
I have no idea how good ChatGTP is on these things, but according to its calculation just now, there should be a reduction down to about 23% of the rate, or reduction by a factor of about 4.4, because of the distance alone. I'm assuming that the distance between the scintillators in 2 detectors there is 1 centimetre. That's probably not right, but just assuming that, and therefore adding 5 centimetres to that would be 6 centimetres. So that's how much you'd expect it to go down by. I can't remember. If I look back at my graph again, I'm not sure whether we could calculate that on there. It says from 0.6 there down to 0.15. What do we reckon? That doesn't sound too far off, does it? Get a calculator. 0.6 divided by 0.15 is 4. That doesn't sound too far off it at all. Almost suggests that the entire reduction is purely on the basis of the geometric effect alone, pretty much.
Another interesting effect you've got there, Andy, is there looks to be like a pulsing going on, quite a regular frequency and amplitude.
I'll pull that back up again. That effect has been mentioned before, and I have no idea why.
Yeah, it's interesting. The frequency it's pretty periodic.
Yeah, there's also a roughly 6-hour periodic frequency as well that comes on it, and likewise I have no idea what that is either. This is
It's going to do with Earth rotation, maybe.
I don't know. This is a Grafana dashboard which somebody else had set up, and we eventually managed to replicate on our computer. I say eventually because it was an absolute nightmare to get it working, but once it's going, it's pretty good.
Andrew, has anyone ever analyzed the effect of temperature on the detection efficiency of any of these muon detectors?
I don't know.
And the reason I'm asking is because of course, what you're detecting is indirect muon passage through the effect it has on a fluorescent dye within the plastic blocks that are then being observed by the avalanche photodiodes. Mm-hmm. And now those fluorescent dyes could have an altered response to the passage of the ionization muons to activate them and give off the flashes of light dependent on temperature. So it's not that the temperature affects the muons or anything else, but essentially the response of the fluorescent dyes within the detector blocks. And so I'm curious if perhaps maybe, I don't know, maybe a variation in temperature in your room can then sort of alternate the response of the detectors So I'm just guessing here, but I'm just wondering if anyone has tested these detectors at various temperatures to see kind of what the detection efficiency changes, if at all.
According, forgive me for quoting ChatGTP again, but it's the quickest way of doing anything. According to that, oceanviewtech.net mentions an analysis which found a roughly 4.4% gain variation over an 11.7% detector temperature range. So
that's with the detectors or for the fluorescent dyes?
it just says of the detectors, doesn't actually say which bit, how they measured those temperature.
Okay.
Without looking at the website itself, I wouldn't know.
Yeah, I see. Okay.
The newer
Anyway,
Cosmic Watch version 3 documentation explicitly mentions logging temperature so that corrections for temperature dependent gain shifts can be applied. Although the correction is apparently not yet implemented in firmware or software.
Exactly. Okay. I thought that might be an influence.
So again, I've not looked at the sources for these, so I don't know. Oh, here we are from ResearchGate. Might be a little bit more sort of, may even, for all I know, be sort of peer reviewed. Another portable scintillator coincidence detector study found a little dependence of coincidence counter rate on modest temperature rate changes, although noting that single channel SIPM rates are more temperature sensitive. So that's an interesting one, suggesting that to some extent the coincident rate is less affected.
I see. Well, the detector itself might have a temperature gain variation.
Mm-hmm.
The actual SIP, not just the fluorescent dye. Anyway, it's interesting that you've had that variation all along on your detectors, and it just seems like an interesting phenomena there.
Yes,
that's sort of regular response.
And as I say, there seems to be something at 6 hours, about 3 times a day as well. So I don't know.
I was going to just put up on my screens a couple of things that I have. Here's a couple of these Geiger-Müller tubes, for example, that the presentation had earlier. I've had a little selection of some of these detectors. I don't know if you guys can see that or not, but there's a couple of these long. They're fairly sensitive detectors. So anyway, I just thought I'd show you those, and I have a collection of some other detectors that I have at home. Here's one of these small units that have been talked about that are fairly inexpensive little portable detectors. So there's one here that has a kind of the glass tube detector on it. I don't know if you can see that, and it's not very sensitive actually. It works, but it's not particularly sensitive. I have a source here that I can, let me turn this guy on. I don't know if you can see that. And here's a radioactive source. I don't know if it'll indicate anything. I don't know if that red LED that triggers it shows up at all.
No, there's nothing seems to have happened that I can see. Oh, hang on.
Nothing you can see?
There's something happened.
Oh, it did? Let's see.
Nothing on there, but your fingers are glowing green, though.
Yeah, well, the green is just the on-off. Let me show you another one. This is actually a much more sensitive one. This is actually one now with a metallic tube that is quite a bit more sensitive.
Ah, yes.
You can see now the flashing light from, and this is I don't know if you can see in the little glass vial is a hand from an ancient watch that had the radium fluorescent dye painted on it so it could be visible at night. And as you can see, it's quite active, even through the glass tube. You can see essentially the detection on it. So this is a much more sensitive tube than the previous glass one. Anyway, I just thought I'd show you that. And I think I've shown you guys before my essentially go-to if I really want to detect something that's radioactive, which is my Geiger-Bueller counter, this guy here, and this is like super sensitive, and so this is kind of my go-to if I want to check for anything to see if it's hot at all, and very handy to have around. Where I live, we used to have a nuclear power plant pretty close by. That's been now shut down. So I was after Chernobyl and some of the other accidents, I always had concern that there might be an accident. And so I had acquired these various radiation detectors just in case anything happened, and I can have some means of being able to establish just how bad the situation was. So fortunately, that power plant has now been decommissioned, and it's been shut down. The reactors have all been shut down, and it's in the process of being dismantled. But it was called the San Onofre nuclear reactor plant, and it's right on the coast of Southern California. And there were a lot of concerns about it. As a matter of fact, the reason it was shut down is because they tried to make it more efficient, and they changed the configuration of one of the reactors, and the configuration, it was a new assembly that developed a leak. And so it was leaking radiation, and the power company decided it was too expensive to correct that, and they thought it's just better to just decommission and dismantle the whole thing. So the San Onofre nuclear power plant is now being totally dismantled, and so I don't have as much of a concern now for accidental discharge of radiation, which is why I collected some of these detection devices. But anyway, I guess they're still handy to have around. Anyway, I just thought I'd show you those little units that I had.
No, that's brilliant. Thanks very much, Adrian. That's fantastic. Can I ask, is there anybody else in this group that has any working muon detectors at the moment? You do, John and Royston. Okay. So which ones do you both have?
I have a Pico Muon system, and it's been recording now for quite a while. And I regret to say that I've done absolutely nothing with it, really. But the data's there. I suppose one day I might have a look at the historical data. And well, one of the things that I thought I might have go at is seeing whether I get the same sort of periodicity that you seem to get.
Yeah, that'd be interesting to hear.
Yeah.
Although I have a Pico Muon, and it's not so easy to see whether there's a periodicity in it, is there?
Well, maybe there's an instrumental difference and effect in there. I don't know. Without having a look at it, it'd be difficult to know.
Yeah.
It's exactly the sort of signal that you would get if you take a purely random set of signal and then put it through a filter. A filter might pick up the certain frequencies.
Oh, right.
So it'd be worth looking at the spectral content of that signal, and that might give you a clue as to what's going on.
Yeah. Okay. I think that's been suggested to me before. Trying to get that data in a format that I can do that with, I've had some difficulty with. I know it can be done, but quite how I do it, I'm not sure. But certainly worth pursuing it, I think.
Presumably, to get a graph like that, you must be making counts within certain time windows. There isn't a chance that the time windows are varying, is there?
I wouldn't know.
Yeah. Okay.
Yeah, I wouldn't know.
Because that's the sort of thing that would give you that kind of response, I think.
Yeah. Okay. Well, thank you for that feedback. Yeah. What sort of detector do you have, Royston?
I have a Pico, and it's been running now for about 3 months. I followed along with your Python course there, and started to do some analysis. I pull all the data off the Pico onto a Linux laptop now, and I put some graphs I did recently on things like pressure, solar flux. I'm going to put those together later on. to try and do some basic analysis on fall-off rates for muons through the atmosphere and stuff like that. But I'm at a very early stage. I can get all the data off the PyCon, because you can't do very much with these Raspberry Pis. They're just not strong enough. So I take them off and I analyze and graph them and process them completely on a Linux machine now. So I replicate it across, and I'm starting to do some analysis on it. That's basically where I am at the moment. So I want to look at things like, you can get a fairly good estimate of things like solar flux from sunspot data, which is reasonably available. So once I've corrected for the pressure and put a barometric factor in it, so I can then start comparing what the muon rate looks like, the basic muon rate looks like, against things like solar flux. And so that's what I'm looking at first, just to see what we can get out of it, really.
If anyone has really tried to establish a muon hodometer setup, rather than these small units from the BAA units.
So what is that? A muon? Did you say pedometer? Did you say?
No, hodometer. HODO.
Oh, right. Okay.
Muon hodometer, which is essentially a multi-sensor device that will now allow you to see the incidence angle of the muon muons that you're intercepting. So not just yes or no, but what directionality they're coming from. And that's very important during, for example, solar storms, where the geomagnetic field of the Earth is being affected, and that alters the trajectory of the cosmic particles that actually impact the atmosphere, thus producing the muons. And so it can vary tremendously from just straight overhead to some angle from the zenith. And so that's what I guess the muon observatories use hodometers in order to measure those angles of arrival. So I'm just curious.
There's somebody from Australia. He uses Geiger-Müller tubes, and he builds a hodometer then he has, I think, 4 or 5 of these tubes oriented this way, and then slightly below he has 4 or 5 tubes perpendicular to them. Then you create a grid.
Exactly.
Yeah. And
so
then you can
on
see the directions. Yeah.
Yeah, depending on the
I
coincidence.
can try to find it and then put it in the chat in one moment.
Well, that would be interesting. But I'm just curious if anyone had attempted that kind of complexity, because it's not just the muon count that's really very important, but the angle at which they arrive that also is significant, especially during solar activity. So that would be actually a much more accurate way to observe that kind of effect. Just curious if anyone had gone to that level of complexity for instrumentation.
I think that would be wonderful if we could do something like that, or one of us could do something like that. Maybe even as a group, we could somehow work together to achieve it. It'd be fantastic. Maybe that should be our long-term aim.
I think I read a paper on it somewhere. I'm trying to find it just then, but there has been some work done on it, but I think it's probably outside the scope of our little organisation here, but there has been some work done on it. It might be interesting indeed. I think that's how we might do a smaller scale.
Yeah, a small scale, even with as minimal as just say 4 detectors for the second plane, or actually 2 planes of 4 detectors.
There's a link in the chat.
Oh, okay. I'll look that up eventually. I have to log that on. But essentially, if you had 4 planes, just 4 detectors for your top set, and then 4 detectors for the bottom, and then you would try to do the coincidence between the angles of any of the any 2 of the matrix. So a 4x4, essentially 2x2 matrix, 2x2 matrix, and then doing coincidence between any given members of the 2 plates would already give you a significant directionality of the muon arrival. So, and that should change dramatically during solar geomagnetic storm events. So that would be an interesting project that shouldn't be too outside the scope of an individual. But
the site I pasted in the chat, he uses 18 of these tubes. So
oh gosh,
9
that's
in each
yeah.
place. Yeah.
Wow.
You would have to have it
But you
more
should
or less
look at his other
three-dimensional.
projects too, because he's quite a genius, I think.
I'll have to look at that. But yeah, something as simple as a double 2x2 matrix, I think, would already give you significant directionality of the arrival angles. So that might be an interesting project for.
You could probably do it, but the calculation, that would be the trick. How to get from basically individual points in a matrix of detectors, working out from that the vectors of where these things are coming from would be quite a challenging task, I think.
Not really. I mean, the circuitry would be simple. You would just simply have
Not the circuitry. Circuitry is not important. It's really how do we calculate these things out. It would be our own little CMC device, I guess.
Well, you wouldn't need a lot of calculation because all you have to do is essentially sectors, right? So you have one corner of one of the matrix on one and the bottom corner matrix of the other, and then that would give you essentially directionality. Are they two from slightly on top of each other, or are they angular? And that already will give you a sector that the arrival comes from. And so you could have a circuitry that would look at the coincidence between any of these 8 different detectors. The four from the top, which one of the four from the bottom. And so the coincidence from any 2 would give you a directionality. You wouldn't need to calculate anything. It would give you a sector. Sorry, you're muted. My apology.
Royston, you're muted. You have to unmute yourself.
I am sorry. I turned it off last time. I brought some feedback. I think it's a good idea to try and put together an approach for that and perhaps present it here as an idea how we might go about it, both in terms of the setup of such an array and how you would handle the coincidences. Because to get the directionality, we have to hit 2 detectors, let's say 2 on a diagonal, to find out the actual direction.
Exactly.
The same muon, if you will. And so that's going to be a bit tricky, but not impossible.
Well, again, the coincidence sort of eliminates the very likelihood of any other particles. So, not exclusively, which is why the 3 Geiger counter in the setup for the chamber is really such an excellent idea. That probability of any sort of statistical triple tube detection coincidence is just really way down there. With 2 detectors, it's pretty good, but it's not 100%.
Yeah, it's a good idea. We need something in this group in general to start moving from just running these little devices and counting, crude counting of data, into trying to do some science experiments. So I'm all for that sort of idea, that now's the time to start moving on a bit and see if we can look at some of the parameters around this. Why not?
I think a simple horoscope would be a very, very sort of doable project. I don't know. Just a suggestion.
Is that something that can be done using those cheap boards off eBay and those Geiger counters?
I think you could use the same basic system that the BAA has. The same. All you need is you need 8 of those detectors.
Yeah, they're £380 or about $450 each.
Okay, well, maybe could use some of these cheap boards.
I know you American guys have got loads of cash, but we're quite poor, cash strapped in the UK here.
We're poor Europeans.
You're thinking U.S. 1985, Andrew, not 2026. Okay. Do you know how much I'm paying for gasoline in California now? Of course, this is dollars.
It's $6.35 a gallon.
Gallon?
I don't know, European. Well, we use a beer gallon. I don't know. I don't know what a liter is. I've been indoctrinated all my life. It's gallons, man.
It's
I don't
about
know.
twice as expensive here, at least.
I think the current price here is about $100 a milliliter. The way it's going at the moment, anyway.
Oh, okay. Well, the rest of the I mean, like in Texas, it used to be like something like $3 or $2.95 a gallon. You know, Texas produces a lot of the oil, and so California has always been more like around $4 a gallon, and just with whatever's going on now, it's shot up to like over $6. So that just gives you some reference, even if the units are not compatible. We started using liters at one time in the U.S. and they took all those gas pumps down.
Yeah.
At one time, they actually had gallons and liters at the same readout, and then something went wrong, and everybody just went, "Oh, we don't know what this liter stuff is." Oh my!
Did you say it was? How much did you say it was? $6? Did you say?
$6.30 a gallon, yeah, whatever that translates to in liters. You can do the calculations. Yeah, compared to what you guys are paying.
3.75 liters in an American gallon.
Okay.
So it's actually $1.68. So yeah, we're running about £1.85, or I don't know, about $2.20, something like that.
Per liter?
Yeah.
Well, anyway, I know it's always been much more expensive in Europe. I mean, U.S. is supposedly the world's largest producer of gasoline, so I don't know, or petroleum anyway, not petroleum. I mean, but see, California is different because we don't have the same system as the rest of the U.S. for distribution. So anyway, it's pointless.
Mind you,
Anyway.
you do have to travel further distances, so I think we have to take that into consideration for you as well.
Sure.
Yeah.
Yeah. Anyway, the detectors in the discussion here to get back to the detectors.
But back to where we were. So we need 8 or 9 detectors.
Eight for kind of, I would say, a minimal photoscope. That way you would get 4 sectors, or maybe 5 vertical, and then 4 angular directions that you could look at.
So you need 8 of them. See you, Royston. All the best to you. See you. Yeah. Bye-bye.
I'm sorry to go into this.
No. So how far apart would these detectors be from each other, out of interest?
Well, just kind of a separation that would be somewhat similar to what you're using now. I mean, it might require a little bit more separation in order to give you better angular sort of resolution, but gosh, it would be something to sort of investigate, see what kind of architecture you would need for kind of a minimalistic photoscope.
I'm thinking 2 of those eBay boards, 2 Geiger counters on top of each other to try and get some coincidence. 8 of those distributed around would seem ideal for Ted with one of his summer students to set up.
Yeah, you could use these guys. I mean, they're fairly sensitive. The only problem is the area. Sensitivity is not the issue. It's just the collection area. With your fluorescent system, you've got, I don't know, a little board like this. I'm just guessing. I don't know. I don't have any of these, but
they're 5x5 boards.
Yeah, so you've got a nice area of collection there. With these guys, I don't know how the collection area would compare to that. But if you had essentially 4 of these on top and 4 of these on the bottom, that any angle between the 2 could be coincidence correlated as to where the direction was. I guess you would maybe have to have 2 in this orientation and then maybe 2 in this orientation. I don't know. Something to research. Anyway, I just mentioned it. I was just curious if anybody had gotten that advanced to where they had thought of going to a directionality and not just rate of detection and number of detection. So that would be one step beyond the simple just yes or no. Yes, we're getting detection, but again, having a second parameter of what angle did that muon sort of what quadrant did it arrive from?
Very good.
And that would anyway, just a thought about that.
Well, if you do that for next month and come and present it to us. Very interesting.
Oh gosh.
I've got some very accurate angles
Have you?
for my system. Oh yeah.
Oh, that's a good
So
point. Yours, you can actually see them coming in, can't you? So you can actually
I can
determine the angle.
actually measure it.
At least you can in one
Get a
plane
protractor out.
anyway. Can you
Well,
do
I
it in the
know
second
it's
plane?
limited in the second plane. It's limited to 7 degrees. So I know that because there are 3, it can't in the one plane. It must come in within a 7-degree plane, and the other plane I can actually see it and measure it.
Mm.
Makes sense.
Yeah. Very good.
Just the only problem is the rate is incredibly slow.
Well,
Again, yeah, the capture really is.
Yeah.
yeah. Okay. Well, thank you very much, everybody. This has been a truly excellent meeting, and gosh, we've gone on for nearly 2.5 hours. That's quite amazing. And thank you very much again, David, for an absolutely amazing talk, and also show around your kit, and then some fantastic videos to demonstrate what you're picking up as well. I mean, gosh, I think we'd all like to have one of those, but looking at all the different bits of it, it's scared the living daylights out of me trying to build one of them, but still, it looks beautiful. What you need now...
Thank you for bearing.
Well, we know from Adrian what you need is 8 of those with 4 on the bottom and 4 on the top. To make them perfect.
That was a wonderful presentation. Really, really fantastic. Very, very, very nice. Thank you so much.
Thank you, and I'm sorry it went on for so long.
You have nothing to apologise for. I think I let it keep going because I think everyone was enjoying it so much.
Went by in a flash.
Yeah, mine in a flash. I don't know how I can beat that at the next meeting, but still. So the next meeting will hopefully be on. It will be on Zoom if it works. So this should be the last time, as far as this Muon meeting is concerned, that we meet on Teams. So I'll send out some links to that to you in the next day or two. And thank you all very much again for taking part. And I hope that you have a wonderful week. Bye bye for now.